advanced lectures to come. So here, this is the more fundamentals which are needed basically in numerical analysis when you talk about the numerical solutions or various techniques for solving differential equations. Well, so in this lecture, I'll brief about the numerical integration, and in particular, though the interpolation I do see will be taught tomorrow, but because I have to talk about numerical integration, so very briefly, not absolutely in detail, interpolation I'll just touch upon, but I'll go through the details of various other techniques, including Gauss quadrature, and then some lights on numerical differentiation in these two lectures. Well, so coming to the interpolation, it's a process basically of estimating values between known data points or approximating some complicated functions by simple polynomials or determining a polynomial that fits a given set of points. So the point is that in various aspects we can talk about the interpolation. So in many applications or from the experimental data, so only the values at some finite points are given, and then we want to estimate the value of that variable at a point which is not known. So that is the technique, it's called interpolation. Other possibility could be that you have a quite complicated function which is probably difficult to handle with integration, differentiation, or getting roots, etc. So this could be also one approach that we can approximate by polynomials through this interpolation techniques. And then once you have the polynomial approximations, then it is easy to deal with all operations, including the numerical integration, which we are going to talk today, or differentiation, that is also part of this lecture. Or you want to approximate the roots, you want to see how that complicated function, going through. So various properties you can actually approximate once you have this polynomial approximation of a given function. Well, so talking to applications, of course, it has a lot of applications. So constructing the function when it is not known explicitly, or only the values of the function is given at some point. The other possibility could be the replacing complicated functions by an interpolating polynomial or simple functions, usually polynomials, so that the operations, as I discussed, such as determination of roots, differentiation, integration, or other such operations may be performed. So that's the idea of the interpolation. The fundamental principle behind polynomial interpolation, if I talk, is this nice result on Weierstrass approximation theorem, which says that suppose this f is a function defined and continuous. So that we are talking about the continuous function on AB. Then for each epsilon, however small, so there exists a polynomial px with the property that the difference between the polynomial and the function you can make as small as you like. So that means that you can approximate a continuous function by polynomials with the accuracy of, or with the desired accuracy. So that is the idea. That means it is possible to approximate any given function which is just continuous by the polynomials. Well, just to recall, though here you need some additional restrictions, but we have also discussed that we can approximate through Taylor's polynomial. So that is also polynomial, and then we can do various operations which I was talking about as a motivation for interpolation. But the point is, in the polynomial, this Taylor's polynomial, this I can demonstrate through very simple example. For example, I want to approximate this exponential function around x is equal to 0. So I want to have this Taylor's polynomial or Taylor's expansion around x is equal to 0. So the 0-degree polynomial is just a constant because that's a function value at 0, which is 1 here. So P0x, we can say that this is just 1. If you look at the approximation, so you have exponential function given here with the red line, and its approximation is given, which is just the 0th order approximation, which is just 1, is given here in this green line. Then if we go for the higher order polynomial, that means this is first order polynomial 1 plus x, then you can see that you have now a slightly better representation, of course, than this P0x. But if you go with higher and higher, for example, this third degree polynomial is here with the black line. So it's approximating this exponential function in some interval around this x is equal to 0, because that was the point of expansion. So here the issue is, or the point is, that the accuracy of these polynomials, even if I go with the higher, for example, the fifth order polynomial, the accuracy is concentrated around this x is equal to 0, which was chosen for this expansion. So that is one point. And the second point is that for this expansion in terms of the Taylor's, though you need the information of the function at one point, we need information only at 0, for instance, in this case, but you need the information of various derivatives. You need information of first derivative, second derivative, third derivative, fourth derivative, and so on. Then you can approximate a given function by a polynomial. So as written here, so the Taylor's polynomial agrees as closely as possible with a given function at a specific point. So they concentrate their accuracy near that point. So the accuracy in all the cases, even in P5, if you say, if you just see here that around this 0, the accuracy is very good. If you enlarge your interval around 0, then you will see here, for example, around this 3, the accuracy is not so good. Well, that you have to go for even higher order if you want to have this larger interval where you are looking at you comparing the two functions. So for many computations, it is more efficient to use this method that include information at various points, and you don't need these assumptions of, for instance, this is smoothness or other the differentiability, and then this interpolation, is more useful than this is, of course, useful in analysis mostly, but when we talk about more practical problems, that these polynomials, interpolating polynomials are more useful than even Taylor's polynomial. So coming to this existence and uniqueness, I'll just brief. I think tomorrow you will have a detailed discussion on the polynomial interpolation. So for n plus 1 data points, so given n plus 1 distinct data points, there is only one polynomial of order less than or equal to 1 that passes through all the points. That's the uniqueness of this polynomial interpolation. As an example, you can always think about that there will be only one straight line. When you have two points, you can only draw one straight line. So that's the uniqueness we can talk about, and then you can generalize the concept. So for simplicity, if we consider for the second order polynomial, so there are three unknowns, A0, A1, and A2. These are the unknowns to define this polynomial. That means if we have three data points, in this particular case, so because we have three unknowns, then we can uniquely determine this polynomial. The idea is very simple, that you just, for example, the 3 points are given as x0, fx0, and x1, fx1, and x2, fx2. So we satisfy each point with this polynomial. So fx0 is given, that should be equal to a0 plus a1x0 plus a2x0 square. So we want this polynomial to satisfy the given data point. So the x1, fx1 point should be satisfied, and the fx2 and should be also satisfied. So we have three equations and three unknowns. So these are the system of linear equations in A0, A1, and A2. These are the unknowns here, A0, A1, and A2. So that means we have such a nice system here. Well, where you can see this matrix A, and then unknowns are A0, A1, and A2, and the right hand side will be given by this fx0, fx1, and fx2. Well, so given this system of linear equations, and one can easily show that this system of equation has a unique solution, because if you just see the determinant of this, which will be non-zero because these points are distinct points, and this determinant is non-zero, and therefore we can say that this has a unique solution. That means given 3 data points, you will get a quadratic polynomial, and that will be the unique polynomial. Well, so in practice, it is observed. I mean, the problem is now why we are talking about interpolation, and then you will have whole lectures on interpolations. Though the idea is very simple, as I just discussed here, that given 3 data points, for instance, you can just get these 3 system of linear equations which has unique solutions. You solve this system of linear equations, and then your polynomial is ready. And the problem is here that it is observed that the above system of equations, so this system of equations, this is for when 3 data points are given, but we can talk about when more data points are given, 10 data points, 5 data points, etc. Here the problem is that the system of equation is ill-conditioned. So we have this ill-conditioning of the system. Ill-conditioning means that if you even have the round-off error, which cannot be avoided in computers, and that error itself will spoil your solution to this system of linear equation. It is so it is highly ill-conditioned system. So we are not talking about more ill-conditioning in this lecture. So whether they are solved with an elimination or any more efficient algorithm use, the resulting system can be the solution of the resulting system can be highly inaccurate, in particular for large n. When we are talking about large n, then this system could be very, the solution could be very inaccurate because of this ill-conditioning, which can be easily checked again with the techniques available. So therefore, we have some mathematical formats which we call like interpolating formats. So Newton's forward difference formula, backward difference formula, divided difference formula, etc. Lagrange interpolating polynomial, in which this calculation, which we are doing here with the system of linear equation, they can be avoided, and that is the whole point of of this interpolating polynomials. And you have in different situations you can apply different interpolating polynomial. I mean, there's different formats. Of course, you will get unique polynomial, whether you use Newton's difference formula or you use this Lagrange formula. But there are situations where we would prefer Lagrange and or backward or forward. This will be discussed, I think, in tomorrow's lecture. So here, my just point is just to have the idea of the interpolating polynomial, and then we will move further. So just to give you some idea in the error interpolating polynomial, since we have a unique polynomial given a set of data points, we have a unique polynomial, then we can talk about error in interpolating polynomial, irrespective of which format you are going to use, whether Newton's forward, backward, divided difference, or Lagrange formula. But this error we can discuss, which is common for all. So I'll not go into the details of the error. I'll just touch upon, because I need that error formula for the numerical integration. So maybe the slides I can share with you. If you want to go into the details, of course, you can go through the proof also. So suppose you have this n+1 data points given, and x is a point belonging to the domain of a given function. So assume that this f is n+1 times differentiable, and this ix, which is the domain here, is the smallest interval containing all these points x0, x1, x2, xn, including x, of course. X is somewhere in between for this interpolation. So then the interpolation error at this given point x, so x is somewhere in between this, it may be between x0, x1, it may be between x1, x2, etc. So now we are talking about that if we want to approximate our function at x, which is not the given point, then how much error we can expect. This error will be given by this the difference between the fx and the polynomial, the interpolating polynomial, which we will see how to get this polynomial. But since it's a unique polynomial for given n+1 data point, then this error is given by this formula, which is listed here in front of you. So this will give you the error here, where this n+1th derivative is used, and also you have all these points x minus x0, x minus x1, and x minus xn, where this xi, which is the argument of this n+1th derivative, it also belongs to the same interval. So this is the error formula, where the proof, as I said, I will not spend much time on the proof because I want to cover more interesting things. But here in this error in interpolating polynomial, I think tomorrow you will go through the details of such error formula. But the proof is also listed here. If you are interested, you can go through. So we have taken like this x, which if it coincides with any of the interpolating node, then of course this error formula already it's a trivial, because the error will be 0. This x you will substitute by any this interpolating node, then this will make everything 0, and the error will be 0. And of course, because this polynomial will pass through the function, will pass through these points, so the actual error is also 0, and your formula is also giving that error 0. So obviously this is what we are not considering. So for simplicity, I mean, this is just the sketch I'm giving you, but not into the detail. We consider this part here, which was given as this x minus x0, x minus x1, etc. Just defining this polynomial by wnx, and then for a given x, which is not the interpolating node, we define this. This is one approach of deriving this error, but there are several other approaches which you can follow to get the error between interpolating polynomial and the function. So I'll just skip this. Finally, I mean, you can show that this error, so you can go through, and in case of any question, I will be happy to answer. So this error between given here fn+1th derivative calculated at some xi, which is somewhere in the domain of these points we are talking about, divided by n+1, and then you have this wn+1, which is just the polynomial listed above. Well, so coming to just, I mean, not again into much details of the interpolating polynomial, but suppose these two data points are given, because I want to have Lagrange interpolating polynomial or any other polynomial, because to define this integration we need this. So suppose I want to fit a linear polynomial, so and two data points are given, so this x0 is given, and also x1 is given there as fx1, and let's consider a polynomial of degree 1. So in this format, because this is going to help us actually, if we take this in this particular form, like b0 and plus b1 x minus x0, but this is just a first degree polynomial. You can take in any other format also, not necessarily in this format. So in that case, what you can fit this given data point. So at this point x is equal to x0, this should satisfy this polynomial. So you can get directly, and that was the reason taking this in this particular format. So when you substitute this, so fx0 should be equal to b0, because x is equal to x0 will make that 0. And in this case, you got already b naught as fx naught. Then at x is equal to x naught point, you again substitute this, and then you will get this b1, because b naught is already calculated as fx naught. So with this, you can easily get this b1 is equal to fx1 minus fx naught over x1 minus x naught. So what we see that this polynomial which we are trying to fit passing through these 2 points is given by this fx naught plus this fx1 minus fx naught over x1 minus x naught, and multiplied by this x minus x naught. Just rewriting this to fit into a very special format so that we can generalize this for any given point. So here what we have this just I'm collecting this with fx naught. So this fx naught, the coefficient is coming to be x minus x1 over x minus x naught. Let me just, I can't see my cursor here. Okay, now it's fine, I guess. Let me just put it again in this format. Okay, so we are here, and as you see now, yeah, so this is with fx naught we have x minus x1 over x naught minus x1, and with fx1 we have this polynomial x minus x naught over x1 minus x naught. This we define as L naught x, and the second one I am just naming it L1x. I'll tell you why. So this L naught and L1, they are called Lagrange polynomial of degree 1, because these are the polynomial of degree 1. And in this special format, that x minus x1 over x naught minus x1 and x minus x naught over x1 minus x naught. So these are called Lagrange polynomial. So indeed now this polynomial of degree 1 can be written as in this form, that we have I moving from 0 to 1, Lix fxi. So Lix already defined here. For L0x we have this polynomial, L1x we have this polynomial. I'll generalize this on the next slide. But this P1x we can write then in this special format. Yeah, so we have this linear polynomial which is called the Lagrange interpolation formula also. So this Lix in this particular case, for when we are talking about just one first degree polynomial, so they are written as in this way. I mean, though there is no product of such here, but since we are going to generalize this, and I want to just quickly wind up this part. So this is taking like j is equal to 0. So you put j is equal to 0, you are getting the first one. And since j cannot be equal to I, so we'll not go with any other. So there's no product as such, only one term will be coming. And when j will be 1, so 1 to 1, then you will get this L1 basically. Well, just generalizing here without going much into the details. So we have the given data points x naught, fx naught, x1, fx1, and so on. For 2, we have seen in detail. But for n also, it is just going to be I0 to n and Lix fxi, where now in this case, this Lix will be nth degree polynomial, and they will be given by this product. So this is like you will go from L0. So in case of L0, your j cannot be 0. It will be from 1 to n, and there will be product of such expressions. So like this, it is given here. So x minus x naught, x minus x1, and so on, x minus xi minus 1, and there will be no term here x minus xi. So except this, all other terms are there with x minus, and in the denominator again you have you can replace just x by xi's. So xi minus x0, xi minus x1, and so on, and that makes this n degree polynomial. So you can have I1, you can have I2, and so on. You can define all these Lagrange polynomial of degree n. So this is what I want to just summarize before we move for the numerical integration. Well, so what we have seen so far, that given 2 points, for instance, you have this first degree polynomial. For given 2 points, you have this 2-degree polynomial, the Lagrange polynomial, and we can extend this as we have seen a very generalized formula on the previous slide. And we have also seen the error in interpolating polynomial, which is given by this expression here, that n plus 1x derivative at xi, which is unknown here, will lie somewhere between these x0 to this x1 point, and the factorial n plus 1, and this product is coming. That is the error in interpolating polynomial. And we can get this interpolating polynomial of any degree, so we can fit this n data points using a similar expression, which is called the Lagrange interpolating polynomial. Well, so this, we now move to the numerical integration, which is the main topic of today's lecture. Well, so why numerical integration? Of course, there are many ways to motivate you for this numerical integration. The one could be that to find complicated integrals like e power minus x squared 0 to 1, where we don't have the closed form of this value, and or there could be many other complicated integrals where you may not be able to find or you may not be able to integrate exactly. So there are two approaches which I am going to cover in this lecture. One is the Newton-Scott integration formula. Another will be the Gaussian integration, formula. So this Newton-Scott integration formula basically are based on the strategy exactly which is discussed there, that replacing the complicated function, or maybe the data is given at different points, with an approximating function that is easy to integrate. So we want to have a corresponding function, for example, corresponding to this x is equal to pi sine square root x, or maybe e power minus x square. We want to approximate this function with basically the polynomial or interpolating polynomial. So that is the whole idea. So we want to approximate this fx, which is complicated and we can't basically evaluate this integral exactly. Then we want to approximate this fx by this pnx. Of course, the accuracy of this numerical integration will depend on the accuracy of your approximation with this pnx, that you have approximated your fx by this pnx, and the accuracy will naturally depend on how good you have approximated your fx with this pnx. So here in general, we can have this pnx nth degree polynomial approximation of this fx, and this is what we call the Newton-Scott's integration formula. A very simple one we start with is the trapezoidal rule, and we are talking about just one application of it. That means we are integrating in a single go with given integral a to b, because there could be various, multiple applications that you can break your integral a to b by several subintervals, and then in each you can again apply the same idea. Well, and then so the idea here is that you have this, suppose this fx function given here between a to b. The value of at a is fa, the value at b is fb, and we want to approximate this by polynomial of degree 1. That is means the linear polynomial. So which is given here by this blue line, that will fit basically these two data points. And then you can see that once you approximate your fx by this polynomial, then the actual integral, which was the area under the red curve, is approximated by this trapezoid. Well, we know what is P1x because that we have just learned in interpolation. So this fx can be approximated by this p1x, which is fa plus fb minus fa divided by b minus a and x minus a dx. And now, because it's a polynomial and we know how to integrate it, so it can easily be integrated, which is given here, that fa and then this b minus a, just the limit. Here you have this x minus a, which you can integrate again this x minus a square by 2, put the upper limit minus the lower limit, and then you will get this value. So what we have fa and b minus a, and then this can be again simplified this further to give you this nice formula, that this integration, if you approximate by just polynomial of degree 1, you will get b minus a fb plus fa by 2, which is precisely the area of this region under this straight line. So given by this b minus a is the width, and then you can just get this fb and plus fa by 2. This is precisely the area of this trapezoid. So here, this is the whole idea, the beginning of the basically the numerical integration, that you can approximate the function by the polynomial. Here we have taken only the first degree polynomial. We have approximated where you need 2 points only. So we have taken the endpoints a and b, and the data is given to you at a, the value is fa, and b is fb, and then we have approximated this integral by this nice formula. So whatever complicated function you have, you need to just get the two values fb and fa, divide by 2 and multiply by this range b minus a, and that will be approximating your integral. Well, if you just want to see just this example, that using this trapezoidal rule, we want to numerically integrate this. Here we have the exact solution also, and between 0 and 0.8. Yeah, we want to integrate 0 and 0.8. So value of f0 is 0.2. The value of f8 you can get 0.232. And if you integrate this, the approximation will be 0.1728. And then you see this, I mean, the integration, the exact value which you can easily get, because itself is a polynomial, it's 1.640433. And this is far from this exact value. The reason is very clear, that you have applied this 0 to 0.8, and all the information of this polynomial is lost. You are using the value at 0 and 0.8. So naturally, we can't expect good accuracy. First of all, if you want to improve the accuracy, we have to divide this interval 0 to 0.8 into several intervals, and then in each we can apply trapezoidal rule to reduce the error. Well, so that's what we want to see, this multiple applications of this trapezoidal rule. That means to improve accuracy of trapezoidal rule, we divide the integration interval a to b into a number of segments and apply the method to each segment. So here, this is the curve, and you have x naught is equal to a here, and this is b, and we have divided into several subintervals. So x1, then you have x2, x3, and so on. So, and intervals. And now the original integral, which was from x naught, which is a, to xn, which is b, we have rewritten as with the property of the integral, of course, that you can write x0 to x1, x1 to x2, and xn minus 1 to xn plus 1. So instead of considering the total interval a to b, we have broken into a small interval, and now we can apply in each this trapezoidal rule. So in each means that fx1, fx0 by 2 into h, then again h into fx1, fx2, and so on. And when you combine this, the formula will be that you have fx naught and fxn. That means two endpoints you have to have, and double of the interior points, because the tuple will be coming here. You have fx1, here also you have fx1. Similarly, fx2 and fx2 will be coming. So they will be these values will be repeated, and fx0 and fxn will be coming only once. So we have this nice formula which can be applied to get this approximate value of the integral when you divide your integral into many parts. So again, written in this format. Well, we have to also consider now, this is the practical approach I have just told you, that how to approximate your integral just by using the idea of interpolation or interpolating polynomial. You can replace your complicated function, and then you can approximate this integral with the help of trapezoidal rule, for instance. Now we want to just discuss, see, because this is a easier case where we can see that how the error will be coming up as a total error in this approximation. For that, we need two theorems. One is this weighted mean value theorem, which says that if we have f and g continuous function and g never changes sign in this range a to b, in that case we can have this integral is equal to fc, and c will be somewhere between a and b, and then you can integrate gx. This is called weighted mean value theorem. I'll skip the proof here. This is not very relevant for this lecture. And there is a discrete version of this mean value theorem which says again that f is a continuous function in AB, and we have this xj's points in this, and cj's are constants, all having same sign, so they do not change sign again, and there exists xi between a and b, where we have, instead of this integral, now we have summation over the cj f xj's, and cj are not changing sign there, the g was not changing sign. So here the other function which was f there, here also f, we can basically take it out, and f will be evaluated at some point xi in this interval, and then you can simply sum the cj as we were integrating there, this g alone. So in particular, if this cj's equal 1 for all j's, then we have this nice result which says that 1 over n plus 1. So it's kind of average of this function, and which will be equal to the function value at some point in this interval a to b. So these two theorems, the weighted theorems, we can or we will be using now in this proof of the error, or rather error bounds for the trapezoidal rule we want to see. So first let's go with the single application, and we have seen already in the interpolation that the difference between fx and p1x, or the error when you interpolate using this first degree polynomial, will be given by this expression where you have x minus x0, x minus x1, and the double derivative at some point t, which is in the domain of our the points. Now we integrate this from x0 to x1, or x1 is, you can consider x0 plus some distance h, and this t depends on x. So this t depends on x, of course, and lies between this x0 and x1, because this t, as I said, will lie in the domain, which the domain in our case is like x0 to x1, and this t will lie in this domain. And of course, this will depend on which point you are talking about for this error. So if you change your x, this t will also change. Well, so our error, which is basically coming because of the difference between fx and pnx, we have approximated fx by pnx and then integrated. So that was the reason of the error, because we have approximated fx by this p1x. So the error we can compute now just by this formula, that you have x0 to x naught plus h fx. This is the actual integral, and minus this was your trapezoidal rule. So this error we are looking at the difference between the two. Well, this can be rewritten as x0 to x plus h, and then you have from this, because this is the coming from the polynomial integration, nothing else. So basically you are integrating this error itself, because here you have the actual integral and the second is the integral of the p1x. So basically the difference will be coming here, which we need to integrate x0 to x0 plus h, and this x minus x0 x minus x1, the double derivative by 2 dx. So this we need to integrate. Well, and this does not change sign in this. I mean, you just note this, that this x minus x0 and x minus x1 will not change sign in this range x0 to x1 or x0 to x0 plus h, because this will be positive always and this will be negative always. So the sign is going to be negative, it will not change. And we can apply this weighted mean value theorem, which was discussed earlier, that this can be taken out, the double derivative, at some point between this x0 to x0 plus h, and then the rest here, this integration, which again, it's easy now because you have only polynomials which can be integrated. So whether you substitute or you integrate directly, one can easily get this error bounds for the trapezoidal rule. So once you integrate this, what we will get the answer as minus h cubed by 12 and the double derivative at some point between x0 to x0 plus h. So this is the error formula for the trapezoidal rule, h cubed by 12 f double derivative. Well, let's just complete first this, that error in multiple application, because usually in practice you will apply in multiple application. You will not just apply once from the given range. So we, as discussed before, that we have to divide into several sections, and then in each section we will apply the trapezoidal rule. That means this error which is coming from each section we have to add, because there will be error in each, though it's small, but we have to add to get the total error. That means we have to add, means 0, the I runs from 0 to n minus 1, and we are adding in each subsection this error, which is equal to h cubed by 3, and then you have this summation there, given summation. And now we can apply the discrete mean value theorem, which I have mentioned there, because there you have one which is not changing sign, and then you can add this one 0 to n minus 1, which will give you just n, and the double derivative will be at some other t here. So we got this, but there is an n here. This, if we are talking about the error, n and h, they are dependent, so we have to convert everything into one. But nh, so n into h, h was the width of each interval, and there were n intervals. So n into h will become just b minus a, which is absolutely free from your h. How many division you consider, it does not matter. So this nh will be just b minus a, and then our dependency is just on h squared. So we have the error, or rather error bound, if you want to get here. So you have to see this double derivative. So if this double derivative has some bound, let's say the maximum value of it is m2, then you can bound this error by this b minus a h squared by 12 and this m2. So this is the error bound in case of this trapezoidal rule. So as you can see, it's a second order accuracy you are getting here with h squared. So you make your h small, your error will be h squared small. So that's the accuracy is of second order in this particular case, and we want to have a higher and higher order accuracy, not just h square accuracy, which can be again achieved by approximating your polynomial with higher degree, not just the linear polynomial. Well, just one example here, and then we'll take a small break after this example. So evaluate the following integral using trapezoidal rule with n is equal to 2 and 4. So you are supposed to take 2 intervals and then 4 intervals and approximate this given integral, which has, of course, exact solution, because we want to see the accuracy and all. But you can, of course, now handle with any integral which are not solvable. otherwise. So find the numerical values, compare numerical values with the exact solution. Of course, we'll do this. Find the bound on the error. So because we know the error formula also, so without computing even the numerical integration, without having this approximate value of the integral, we can directly use the error bounds which we have just derived to give the idea that what will be the upper bound on the error. Also, there is a part here that we can also use this error bound which we have just derived to get the number of subintervals required if we have some information or we have some desired accuracy that the error should be less than some given number. In that case also we can use this error formula to get the number of intervals we should take to achieve this accuracy. Well, in this example we will see. So the number of subintervals 2, that means your h is 0.5, that means you are going from 0 to 0.5 and 0.5 to 1 to 2 intervals. So 0 to 0.5 one interval and 0.5 to 1 another interval. And then you apply your numerical integration formula. So 0.5 by 2, f0, and 2 times this f in the middle point. So as discussed before, double of all the interior points, and the f0 and f1 are the extreme points. So you substitute these values and then you will get the answer point 25833. Well, we can continue with this having the number of subinterval 4, and in that case your h is going to be 1 by 4, and hence we can now apply again the same formula. The extreme points will be counted once here and then 2 times all the interior nodes, and then this calculation will give us 0.25 and 15. So these are two numerical values we got with two different number of intervals, and the exact solution is 0.25541, so pretty close to what we have. The error, if you just see, I mean the actual error, because we have now the numerical value also, though we can estimate through the given error bounds, but now we will justify that these error bounds will be actually the correct error bounds. So here we have the error with first attempt where we have done only 2 subintervals. In the second case, we have this error 0.00074. But these error bounds, with the help of this error formula, which we have just discussed before, b minus ah square by 12 m2. So m2 is the double derivative. So you have to get some estimates on the error bound on the double derivative. So this is your fx. You can get the first derivative, you can get the double derivative, and in the given range of 0 to 1, as you see that this maximum value will lie at in one of the boundary points, but this x is in the denominator, so this maximum will achieve when you have this x0. So then you will get 8 over this 27 will be the maximum value of this, and then the error will be bounded by this b minus ah square by 12 m2, and if we substitute all these numbers here, h, b, and a, and m2, which is we have the estimate on this, because we can't get exactly the exact error by this. These are the bounds you can get through this error formula, and because of the unknown which was in f prime, f double derivative at some xi unknown, it has to be calculated, and that unknown varies depending on various factors. So what we can do, we can only estimate the double derivative in the whole range. And having said this, we have this 1 over 12 h square 8 by 27 and h 0.5 in the first case. This result says that your error will be less than 0.0067. And what was the actual error? Actual error was 0.00292. Of course, it is bounded by this one. In the second case, when h was 0.25, and we say that this error will be by this formula, should be bounded by 0.00 and 154. And again, this is true that because actual error was 0.00074. So again, here we have verified that this error bounds are the correct upper bounds, and in both the cases we have seen that the actual error is bounded by these numbers which have come directly without calculating the numerical integration. In the third part of the problem, it was given that we have some desired accuracy, let's say 5 into 10 raised to the power 4. We want to have the accuracy in our approximation less than this. So we have this error bound. The error bound says that this error should be less than this, and with this information we can get h, or the number of intervals we should have in our approximation. So you just substitute all these numbers there, and we want this to be less than 5 into 10 raised to the power 4. So see, everything b, my, etc. are known. I mean, these are knowns. Only the n you have to see which satisfies this inequality. And with this some simple calculation, you can find out that n should be greater than 7.303. So n is a number. So if you take n anything larger than 7, you can take 8, you can take 9, you can take 10. In that case, your error in your numerical approximation is going to be less than 5 into 10 raised to the power minus 4. So we require minimum number of subintervals 8 to make sure that this error is bounded by this one. And let's take just 5 minutes break, and then we will continue this idea of numerical integration, which we have started with a very simple thought of linear approximation. But of course, to have higher order accuracy, we have to go for higher order interpolating polynomial. And if we go with the higher order interpolating polynomial, then you will see today that we will get the Simpson's one-third rule with the same idea which we have just completed, including the error. So let's take just 5 minutes break, and we'll be back again.
Yes, participants, as suggested by Professor Jitendra Kumar, we will be taking a break of 5 minutes. And I hope you people had a good last 1 hour. Professor Jitendra Kumar has taught you about the polynomial as well as the numerical integration, mainly about the trapezoid rule, where we are considering the small trapezoid to find out the area. And I suggest all the participants to actively take the keen interest in understanding these numerical methods, because tomorrow I'll be taking another lecture in the first half, where I'll be teaching you how to write a C program for these methods which we are using to solve numerical integration, like trapezoidal method, Simpson 1/3 rule, Simpson 3/8 rules, and other methods. So now you try to understand the mathematics of all these problems, and then tomorrow in the morning, in the forenoon session, we will try to write the C program for these methods. Thank you.
Okay, so hope everyone is back now and we can continue. So in case you have any questions so far, maybe it's better to discuss if you have anything where you feel confused or I was too fast, maybe. So we can discuss first and then we can continue.
Yes, Professor Jitendra Kumar. So all the candidates, if they have any question, they can write in the chat window.
Okay, perfect. Yeah, that's nice. Okay, I'll open my chat window also.
Yes, sir. Because it's a one-way system. You can speak with them, but they cannot directly speak in their.
Okay, but they can write down. Yeah, fine.
Yeah. So they will write whenever. I request all the participants, whenever you have any question, you can write in the chat window. And Professor Kumar, my students are there. Whenever there will be any question, they will remind you in between of your talk also.
Okay, perfect.
Yes.
Very nice. So I can continue, I think now, right?
Yes, sir. Please, sir. Go ahead.
Okay, thank you. Yeah, so now we are talking about the Simpson's 1/3 rule. And in this case, this function which we have approximated by linear polynomial, in this case, we will go with P2, so the second degree polynomial. That's the only difference. Otherwise, the rest everything is same. So now, because we are talking about second degree polynomial, we need 3 points. And then you will have unique second or less degree polynomial. Well, so we have just P2 is replaced by here, which was again summarized before that this interpolating polynomial we have discussed. And then you can easily integrate it. I mean, those steps I can leave because see, otherwise it's nothing absolutely. You have this quadratic polynomial which you need to integrate here. You have here also quadratic polynomial, here also quadratic polynomial. Fx0 anyway constant, fx1 is constant, fx2 is constant. Denominator is also constant, so you need to just integrate this x minus x1, x minus x2, and similarly at all other places. Well, so once you integrate, again, I mean, this is not so important that how that I explain you that how you integrate. You can do at your convenience, whatever. But finally, what will come after this integration and then putting the upper limit, lower limit, you will get this nice formula that h by 3, the function value at the first point, x0, 4 times fx1 and the end point. So first and the last point here, we were integrating from x0 to x2. So first point, the function has to be evaluated. At the end point, it has to be evaluated. And 4 times in between. Well, so this is, we call single application because we are just considering that we are integrating x0 to x2. And this is called Simpson's 1/3 rule. So earlier it was trapezoidal rule. Now we have Simpson 1/3 rule, and you can actually continue this. So you can have third order polynomial, fourth order, and so on. And every time you take the higher order polynomial, it is expected that you will get better accuracy. Good. So let's talk about the multiple applications. So now in this case, we have divided into several intervals. So x0 to x2, because you need 3 points in one application. You need x0, x1, x2. Then here x2, x3, x4, and so on. So you need a block of these 3 points you have to consider. That means 2 intervals you have to take. And then you can apply again this Simpson 1/3 rule in each. So you have 1/3 h and fx0 4 times the inner node, so that is 4 fx1, and then fx2, the outer one again. And same thing you will continue with the second integral, then third integral, and so on up to the end. But in each case, you should have 3 points. 2 endpoints, 1 in the middle. That means two intervals. Well, and then you can combine it because this fx node is coming in this first integral as well as in the second one. Similarly, here fx4 will be coming in the next integral, etc. So we can have that 2 times this 2, 4, 6, and so on. and 4 times these odds, so 1, 3, 5, and so on, and the first and the last is just once because they are not repeated anywhere. Well, again, I mean, I am skipping this, but exactly the same idea what we have followed. We have the error between this second order polynomial and the function, which you need to integrate it. And after that integration, applying those weighted mean value theorems, we can get that in the single application, you will get H5 over 90 and F4 fourth order at some xi point, or multiple application, usually one order is reduced here, so it was H5, you will get H4 because this B minus A as a constant term will appear here. So now it is depending, the error depending on H4 in this case, and of course this fourth order derivative. So again, the idea is same, that if you have bounds on this fourth order derivative in the given range A to B, then we can have the the error bounds for this Simpson's 1/3 rule. Well, let's take the same example using Simpson's rule. Again, you can take N2, that means just one application, and 4 you can apply 2 times for the same 0 to 1 and compare it with the exact solution. So when you take n is equal to 2, that means these 2 intervals, the minimum requirement for applying the Simpson's rule. You can have 2, you can have 4, you can have 6, you can apply in that case any multiple of 2 this intervals. If you have, then you can apply the Simpson's rule. So here you have h by 3, you have f at 0, the 4 times f half, and then you have f1, and just substitute these values here and we get 0.25556. And when you take these 4 intervals, in that case again you need to calculate, and you will get of course better result, which is 25542. Okay, the exact solution was 25541, and you can compare. In case of the trapezoidal rule, we didn't get that good results. Now in Simpson's, because this is more accurate and we are getting the better results. If you see in this n is equal to 4 case, though there also we have taken n is equal to 4 intervals, but then in each interval we have applied the trapezoidal rule. But now again 4 intervals, and you see the result is almost matching with your exact solution. So of course this is more accurate than a trapezoidal rule. The reason is clear, that you are approximating with higher order polynomial, which approximates better your function. Yeah. Okay. So numerical integration again, if I just summarize here, that the trapezoidal rule we have just gone through, where you have seen that you just need to get fx naught and fxn, and all intermediate nodes you can sum up with multiplication of 2. The error bounds we have seen, the error was second order accurate in this trapezoidal case, and if you go for Simpson's 1/3 rule, then the accuracy is the 4th order. Well, there is another version of Simpson's 3/8, though 1/3 is more popular for some reasons. I'll tell you why. Because in this case, the idea is to continue with this with 3rd order. So replacing our function with 3rd degree polynomial, that means you have to take now 4 points. So you have x0, x1, x2, x3. That means 3 intervals. Yeah, 4 points means 3 intervals. And in this case, your intervals has to be a multiple of 3. Like in Simpson 1/3 rule, it has to be a multiple of 2. So now, again, I will skip this because there's just a simple integration of quadratic polynomial or cubic polynomials, and then you will get this 3/8. So 3h by 8. In case of 1/3, it was h by 3. Now we have 3h by 8 factor there. You have fx naught and fx3 as the endpoints. Always you see ones. The 3 times this fx1 plus fx2. So you need more number of intervals for a single applications itself. The error in this application will be again H5. So we did not gain much here. In 1/3 also we have the same H5 in single application, and in composite rule again you can just add these fx to 3, 3, 6 and so on. They will be coming with 2 times the 3 times these 1, 2, 4, 5 and so on. And well, so in this case also the error is H4. So what we see, whether you apply 1/3 or you apply 3/8, the error is of order 4. So why to go for the 3rd degree polynomial when we can achieve the same accuracy with the 2nd degree polynomial, just considering 2 intervals. Here we have to have multiple of 3. So either you can work with 3, you can work with 6. There in 1/3 rule, you can work with 2, 4, 6. So you have more flexibilities and same accuracy. So therefore, the Simpson's 1/3 rule is more popular, of course, than the 3/8 rules. But you can apply 3/8 as well, and you will get actually similar accuracy here too. Well, there are many other versions of it. These such rules here, like midpoint rule we call. So fx you can just approximate in the middle and then multiply by d minus a. So you are getting another kind of approximation. This is called midpoint rule, which you can easily get if you just approximate this fx by this Taylor's polynomial. And then if you integrate this, then you will get the first part here, fxi and b minus a. Xi is somewhere in between, so this is the middle of a and b. So you are getting this, which I'm calling like a midpoint rule, and then the rest will go to the error part. And the interesting here is that this error, if this becomes 0, and then you get basically the higher order than expected. So you get here this H3 again in single application, or in multiple application you will get again second order accurate, like trapezoidal rule. So this is another possibility of instead of taking trapezoidal rule, if you apply midpoint rule, which takes only value at 1 point. Yeah, not at many points, not at 2 points, only at 1 point, but you can still get a similar accuracy what the trapezoidal rules offer you. So you can, instead of trapezoidal rule, you have a possibility of midpoint rule, which is much simpler, of course, than the trapezoidal rule. So as I written here, the error in composite rule here is of h square. So there also it was h square. So this is another version where we can derive using this Taylor's polynomial, not just the interpolitic polynomial, but using the Taylor's polynomial, we can also derive this, which is just the midpoint rule. Well, so if I summarize here, the trapezoidal rule and the midpoint rule, they are second order accurate. So you have possibility of using any one of them. Though if you go more in absolute sense, this midpoint has even less error. It shows less error because h square by 12 and here h square by 24. But overall h square, so it does not matter much what factor you are getting there. But overall both are of second order accurate. Whereas the Simpson 1/3, Simpson's 3/8, you have the fourth order accuracy, which is good enough to approximate your integrals, and therefore we don't want to go for even higher order, maybe fifth and sixth order polynomial you can use there and achieve even higher order accuracy. But fourth order accuracy is good enough, and then of course you can increase your accuracy by taking more and more number of intervals. So even with trapezoidal or midpoint rule, while taking, you have to take maybe a lot of intervals, you can achieve your desired degree. But there are problems to have more number of intervals, basically that you will be computationally more expansive, your computation will become more expansive, and at the end, more function evaluations will lead to more kind of round of errors, etc. I'll talk a little bit towards the end just to give you some flavor of that we should not do too much evaluations. We try to make as simple as possible, as less evaluation, function evaluation as possible, and therefore these higher order methods must be used instead of using these low order method and taking so many intervals. Better to take less intervals and apply higher order methods, so they will give you better accuracy. Well, just to give you some idea, though we have discussed in detail this Newton's Cotes formula, which was trapezoidal rule, which was Simpson's 1/3 or Simpson 3/8 or midpoint. So two I have listed just here in front of you. So the Newton's Cotes formula, if you just see, they can be expressed in this form. In general, if I write that there will be some constant and there will be fxi. You will be evaluating a multiplying by function at some point and by some factor, which factor may depend, like here you see this h/3 with the first fx0, then you have 4h/3 with these odds ones, and then 2h/3 with the evens, and then again h/3 with this. So, but in general, the structure is of this form, or in this format, we have all these methods which we have discussed, that ci fxi, some constant into fxi, we are evaluating or we are approximating our integral in this form. So Newton's Cotes relies on picking equally spaced points. That is a key point which I think you can, if someone asks you that what is the basic difference between Gauss quadrature and the Newton's Cotes formulas. So the basic difference is that Newton's Cotes, they rely on picking up equally spaced points. So if I ask that you get 10 points in this interval, or you divide into 20 intervals, meaning that equally spaced grid points you are making there. But the Gaussian quadrature basically picks the best point. So this, like we have seen so far, there is a factor h, which is the spacing between the two grid points. And in all these formulas, in all these Newton Cotes formula, you do see h. That means they rely on equidistant grid points. But the Gaussian quadrature, this is again very beautiful way of approximating your integral, is to pick the best point, because these equidistant grid points may not be the best, because they will be less in number. If you pick the best, you may get less points in number, meaning less function evaluation. As I just indicated before, that our aim is to have minimum function evaluation, just to have computationally better computationally expensive. We don't want our algorithm to become computationally expensive, and also the error overall, because of various factors. One I told you already, surrounding of error is included more if you have more function evaluations. So for better speed, we need to pick the best point, so that we need minimum number of function evaluations. So the idea of the Gauss quadrature is as follows, that how to choose weights. The idea is a similar one, that we want something ci fxi. See, in the previous case, we have also some constant into fxi. We still want to have the same thing, but now we don't want equidistant these nodes. We want to have best nodes, so that we get best accuracy. But the question is that how to choose these ci's and xi's, so that this provides a better approximation than earlier, or good approximation of the integral. The first idea here, don't think it's too complicated. It's very simple. We want to first convert our interval a to b into -1 to 1, because once our integral is -1 to 1, then we will discuss that what are the best points to be picked in -1 to 1. So you can always, given an integral, you can of course do this transformation. It's not of course difficult. So you take x is equal to b minus a/2 t into b plus a/2. With this transformation, you can convert your integral, whatever your integral a to b fx dx is, into some integrand. Of course, this integrand will change a bit, and -1 to 1 and dt. So this step is, I think, clear that any given interval a to b, by this simple substitution, you can convert exactly that equal to -1 to 1 and in this. So now we will discuss for this Gauss quadrature how to deal any integral which is given in -1 to 1. Okay, so how to find the nodes? So this is the whole idea now. -1 to 1 fx dx we want to integrate. We want to find x1 and x2. We want to find c1 and c2. So this x1, x2, what are the best x1, x2 to be chosen? Like in trapezoidal, what we have done, it was like the first point and the last point was chosen. And then we got the second order accuracy. Now we want to again have two function evaluation like trapezoidal rule, only two function evaluation, but not at the end points. We want to have somewhere else which can provide us better accuracy. So we have the four unknowns now. We have C1 unknown, we have C2 unknown, and we have X1 and X2, two unknowns. Well, one way is to choose theory of orthogonal polynomials, Legendre polynomials. So there is a whole theory behind this, the Gauss quadrature. And again, it's not possible to explain the whole idea. So I'll take a better way where you can at least get the idea for those who have not gone through in detail about the Gauss quadrature. This is called the brute force method. That means we set up equations for CIs, XIs, such that the 2m points, suppose we have the CIs and XIs, so 2m points, guarantees that polynomial of degree 2m minus 1 are integrated exactly. So we have here 4 points, 4 unknowns, C1, C2, X1, X2 in our consideration at this moment when we want two function evaluations. Well, so in this case, what we want to have these like 4 points. We want a 3 degree polynomial to be integrated exactly. So there it was like linear polynomial we have considered, which was integrated exactly. Now we are going with the third degree polynomial for this particular two evaluation case. So this C1, C2, X1, X2, the idea is explained for just this simple case, but you can extend it for more points. So the C1, C2, X1, X2, such that the method provides exact integral for 1, the constant. It should provide you exact integration for x. It should provide you exact integration for x squared, and it should provide you exact integration for x3. These are our conditions. Because you have 4 unknowns, we need some kind of 4 conditions to be set up to solve this overall these 4 unknowns. So the idea is that our integral should be exact for polynomial up to degree 3. And by doing so, if we do like f, we want that if we take the constant function, it should give you the exact answer. So here you integrate this 2, and then you have C1 and plus this C2. For fx is equal to, so why C1 and C2? Because your function is constant function. It's just 1. So fx1 is 1 and fx2 is also 1. So you get this equation simply C1 plus C2 is equal to 2. We got one equation. If you take fx is equal to x, again, it should satisfy the equation. So you have 0, and the right-hand side will become C1x plus C2x. So the second equation we got. The third equation, again, with x2, you will get the last equation, the fourth equation, you will again get while integrating this x3, which will give you 0, and the right-hand side will be C1 x13 plus C2 x23. So the idea is simple. You want the structure to be C1, some constant fx1 plus constant fx2. Since there are 4 unknowns, you want your integration exact for constant functions, for linear, for quadratic, and for cubic. And these 4 equations to be solved. So that's a big challenge. If you have more equations, the solution, of course, is difficult. For this set of equation, it was not so difficult, or it is not so difficult. You can easily get solution of this system of equations as C1 is 1, C2 is 1. It will satisfy all the equations, if you take x1 minus 1 by 3 and x2 is equal to 1 by 3, it's a unique solution. You don't have many possibilities. You get unique solution out of it. And now we got, see, the x1 and x2, the two function evaluations will be done at minus 1 by square root 3 and 1 by square root 3. And these c1 and c2 are just 1. Now, if you compare to the trapezoidal rule, we were evaluating our function at 2 points, at end points. Now we will be evaluating again 2 times, but at these 2 points here. So this is the formula, that you evaluate your function at minus 1 by square root 3 and 1 by square root 3, add, that's all, done. So beautiful. Similarly, you can extend this for 3 nodes. That means you have 6 unknowns and you have to go now up to degree 5. So 1, x square, x3, x4, x5, and you can actually do so. So you have these 6 equations and you can solve it. And again, you will get this c1, c2, c3, x1, x2, and x3 in this way. So we get this formula as just 3 evaluations, and we got this formula here now. And the accuracy is of order 6. And earlier it was up to 3, so accuracy was up to order 4. There is a I mean, if you go on keeping this system of equations which are not so easy to solve. So there is another theory which I'm not going into the detail, but using Legendre polynomials and all, you can actually get all these unknowns easily. So this is the so-called Legendre polynomial. So the weights means, yeah, these coefficients. So the weights, yeah, yes, exactly. So there was a question here. So weight means these weights, C1, C2, C3, these are the weights, and these are the nodes, X1, X2, X3. So these all 6 are unknowns which we need to get using the system of these equations we have to solve, and there will be a unique solution. Of course, this is not so easy to solve, and therefore I'm just giving you some idea that about this theory where you can have, the generalization to more nodes and so on. So this is a Legendre polynomial. And so again, looking complicated. So if you go with P0 x, it's 1, P1x is just x, P2x is again here, P3x is given here, P4x is here. So that's 4 degree polynomial I have shown you. And the idea why I'm showing you here, so this we have seen that considering only 2 nodes, our formula was f minus 1 by 3 and f 1 by 3. Considering 3 nodes, we got this formula, just solving those equations and so on. The idea is as follows, that these CIs, those weights sitting there, those coefficients, those CIs can be calculated by this formula. So without, going through all the details of solving linear equations, etc. So we implemented so I'll go through these questions a little later. Let me just complete this. You can keep on asking. We can go through at the end. So CI is given by 2 over 1 minus xi square, and this derivative of these polynomials is square. So these are the CIs you can calculate from here. Let me just. So the nodes of the Gaussian quadrature are the roots of the Legendre equation, these Legendre polynomials, and weights are calculated. I mean, the CIs are calculated by differentiating polynomials and nodes and using the above formula. So these numbers 1 by 3 and 1 by square root 3, these are the roots of, for example, here the P2, the roots of the P2, you will get these 1 by square root 3 and 1 by square root 3 minus and plus. When you go for the 3 nodes, you can get these from this 3rd degree polynomial. From 2nd degree polynomial, 2 roots. From 3rd degree polynomial, you get 3 roots, which are given here as minus square root 3 by 5, 0, and 3 by 5 square root. So, and the CIs you can get directly from here. So there is a nice theory in the background which we are not touching upon, but instead of following that approach which we have just discussed, that you set up those nonlinear equations, solve them, which is very difficult, with this formula, and with the help of this Legendre polynomial, you can actually get easily the next formulas. For example, 4 points you want to take, 5 points you want to take, you can get with these, the roots you can get easily from here. For example, you want to extend to the fourth, you can get roots of this fourth order polynomial, and the CIs you can obtain from here. So that's the idea in the background, which I'm not going to detail how this derivation is done with this Legendre polynomial, etc. So if just an example, if you want to just evaluate this using Gauss and compare it with trapezoidal, why I want to compare it with trapezoidal, there also the number of evaluations are 2, for example. So the exact value is given also, is 711.7118. And if you see this table, so the function evaluation, I want to have 2 function evaluation. If I use this Gauss quadrature, my answer will be 0.6979. And the error is just 1.9%. If I use the trapezoidal rule, the accuracy will be, the error will be 200%. So it's 0.71 was the exact value, and here you have 2.1852 will offer you this trapezoidal rule, having the same, computational expenses. That means the 2 function evaluation. Anyway, Simpsons we cannot do with 2 functions evaluation. Let's go with the 3 function evaluations, where we can use the Simpsons also. So it is given here. This Gauss quadrature will give you 0.7149 with 3 evaluations, 0.4% accurate, very accurate. 7118, it was 7149, you are getting the answer. Trapezoidal, if you use with 3 evaluations, correct, then you will get 1.0926, 54% error. Here error is very, very less. And if you use even the Simpsons, which is also the accuracy is high there, you get a 0.7284, not acceptable as this Gauss quadrature. So therefore, this accuracy is really high in this Gauss quadrature with, if you compare with the computational expenses. So so this is one of the the widely used quadrature rules, the Gauss quadrature we can use. So with this, I can stop with this, this numerical integration, because I want to give you some idea. It will not take much time. We are running out of time with the numerical differentiation as well. So the numerical differentiation, again, there are various approaches we can derive those. We can get again approximation of numerical differentiation. One approach could be like numerical integration, that you approximate your function by the polynomial, and then you can integrate, or you can differentiate those polynomials, and then that's all. You get this numerical differentiation. So this could be one approach, because polynomials can be differentiated easily. But we will rather derive here using Taylor series expansions, because this is more general approach and better approach somehow. So the popular, most of you must have heard about the forward difference formula. So I'll just quickly go through here. We'll save some time. So you have this Taylor's expansion around x0. So you take, we want to get the derivative approximated at x0. So y x0 plus h, in the point in the neighborhood, x0 plus h. Let's take positive here. So y x0 plus h is equal to y x0, and so on. You can just see this Taylor's approximation. And if you just take this to the left hand side, that is y x0 plus h minus y x0 divided by this h, then the right hand side will be just the first derivative, and then you will have this h by 2 and y double derivative at x0. Well, so if we just leave this error part here, we just consider this h by 2 y double prime as error, then we can say that this y prime can be approximated by this difference y x0 plus h minus y x0 divided by h. This is precisely, we have the first formula to approximate the derivative. So this derivative can be approximated at x0 by yx0 plus h, you take a point in the neighborhood, yx0 plus h, minus subtract the yx0 and divide by h. This is called the forward difference approximation of the first derivative. The error in this case, because the error term is clearly written here, h by factorial 2 y double prime x0 plus, of course, more terms there. Or you can stop it here by not saying x0 here, but putting some unknown xi. You can also stop this formula at this place itself, and then this will become error. However, the error, the order here is h. You see the leading term is just h. So the order in this case is 1. So this forward difference formula is first order accurate. If you just want to see this geometrical representation, so suppose this green one is our function here, and at x0 you have some actual derivative. I've just drawn this tangent there, so that will give you the actual derivative of the function. But we want to approximate numerically, that means with the forward difference. So we have to take a point x0 plus h, its function value. And if you see the derivative here is approximated by this, so that is the exactly the tangent. I mean, this was the actual tangent there, and this is approximated by this slope of this line, which is dotted green line. So because this is f or yx0 plus h here minus this fx0, so basically this difference will come here and divided by h. So this is the slope of this line. So we are approximating this slope of this line by this slope of that line. So you see this how weird it is, because it is if I have taken this h0 a little far here, and then you see, okay, I mean, it's not giving basically any approximation to the slope of actual slope. It is completely different. But if you take h small and small, suppose you are very close to this point here, then you will see that it makes sense. So of course this formula is just first order accurate. So depending on the error depends exactly on h, and if h is large, so this error is going to be very large, and therefore this is I mean, not widely used as first order approximation. We'll go for the higher order approximations, and we'll see little later. So this is, but however, very important to begin with. This is a forward difference formula. Again, a similar explanation can be given for the backward difference approximation. So instead of taking a point in the forward direction in the neighborhood of this x0, you can also take a point in the backward direction. That means you need to now apply this Taylor's theorem on x0 minus h. If you do so, and then again divide by h, and you will see this, that y prime can be approximated by this difference here, and then the error is again of order h, so no improvement in terms of the error, the same situation. But instead, because there are situations sometimes that you don't have a point right to this x0, you have only point left to this nitro, so you have to apply this backward difference formula to get some approximation there. For example, you will be solving differential equations, and at the right boundary, that is the end of this your domain, you don't have anything right to it, because this is the last point and you have only the points or the data available left to it. So if at all you want to approximate at the right boundary your derivative, you have to go to the left, and then you have to apply this backward difference formula, not the forward one. Similarly, at the other end, at the first boundary, you have to apply the, for example, the forward difference formula you can apply, not the backward. So therefore both are important, but this is also first order approximate, and the similar explanation you can see here, x0 minus h, and then this line joining this point is actually approximating that actual derivative. And again, in the picture you see that they are far from each other, which is fine because you have first order accuracy, and my h is pretty far from here. But if your h is very close to the x0, and then you will see that you will get good approximation. So it depends on the approximation, will depend, of course, how far is your h. And indeed, you have seen this in the definition of the derivative when we began with that what is derivative. It's actually the limit of this, limit as h approaches to 0, then you will have equality. So we have removed that limit and then we have the approximation. Yeah, this is what also you can understand this in this way. Good. So just to move on, we have also another approximation of this first derivative, which is the central difference approximation, which is higher order indeed. If you consider these two Taylor's expansion, one is for x naught plus h and x naught minus h, which were used for forward difference and backward difference formula. And what you can do, you can basically subtract the second one from the first one so that this y x naught will cancel out. The y prime x naught term will be added. This will be again cancelled. The h3 powers will be added again. So what you will get when you divide by this 2h, because this will become, when you subtract this will become 2h y prime, and then 2h you can divide here, and this is the expression coming up with first order derivative. And now you see you have the higher order term coming up here, not just the first order term, which was the case earlier in both the formula, but now you have second order term here. And this first derivative is approximated by this difference yx naught minus h minus yx. This is yx naught plus h, sorry for this typo. And then this error, which is the leading term, is of h squared. So that error is basically of order 2 in this case, though we are talking about the first derivative itself. But with this formula, you can get the higher order. But you are considering basically 3 points. You are talking about x naught, then you are considering x naught minus h, and you are also considering x naught plus h. Well, so this is second order approximation. And in this case, if you just see that this quotient here is nothing but the slope of this line here, the green dotted line, and the actual derivative was here. Here you can see little, in this particular situation also, that yeah, this is making more sense than the earlier one. They were very far away, but now you have pretty close, slopes of these two lines. But anyway, it depends on what function you have chosen. But in any case, this central difference, it's a second order accurate, so will give you certainly a better accuracy than those first order formula. Actually, you can get many other, it's not just, you can get like forward difference extended to further points. So again, I'm not deriving here, but you can easily do that. You just write down the Taylor series for x naught plus h, x naught plus 2h, and then with this particular combination, if you add, then you will see that you have 2h and y prime sitting in the right hand side with the higher order, again the second order accurate. So if you take, instead of this is also considering 3 points, this is also considering actually 3 points, but in one direction, because as I mentioned you before, in some situations you can't go to both the directions. If you are sitting at the end points, you have possibility of going one-sided, and then you have to use maybe the forward difference here, like forward difference type formula, or maybe backward difference formulas can be also derived in the similar way, and which are higher order accurate, not just first order accurate as before. You have higher order accuracy. So if you want to maintain the second order accuracy for first derivative, either you have to use the central difference, wherever there is a possibility that at given x naught you have a possibility of considering to the right, considering to the left, then you can use this second order approximation, which is good. But in some situations where you do see that you can only go in one direction, that you have to use either this one for the forward direction, or a similar one where you will see this x naught minus h, x naught minus 2h, etc. That also can be used at that point, again maintaining the second order accuracy. Well, the central difference approximation, the second derivative, again you have, so for the second derivative you have these two Taylor's approximation. If you add them, you will get this nice formula again here, x naught plus h minus 2yx naught and plus y x naught minus h over h squared. and then the right hand side you have this double derivative, and this is the error contributing to this h square by 2. So which is precisely that this double derivative we can approximate by this kind of central difference formula, and where there you can maintain again of order 2, the accuracy of order 2. So there are various variants, not only just 2. This was just to introduce you that, well, with the Taylor series itself you can get these approximations. Some of them we have derived here. There are many other possibilities to have the second order accuracy or even higher order accuracy, not just the second. Even in the first order you can get fourth order accuracy by choosing the proper combination of taking more data points, of course, not just the 3 as we have taken. You have to take maybe 5 data points and you will get fourth order accuracy. And there are various such difference formulas available in any textbook you can go through. Well, so this is second order accurate. So there is not much, time left, and I don't want to discuss more on these numerical differentiation. But I will end just there are 2 slides where you will get some, more flavor on that. It is not just what we see that there is something more which contribute to the error. So that I will not only just the error I was showing you, which is coming due to the truncation of the Taylor series, etc. But in general, there is something else which is called round-off error, and it has a very big impact. In this example, I'll show you, if you consider just this 4th degree polynomial, just give me 5 minutes and I'll wrap it up. Its derivative, that is 4x cubed minus 3x squared minus 2x minus 1. You approximate the derivative. We know now how to approximate. Let's take forward difference. You can take backward difference, or you can take central difference, or whatever, any other formula of higher order as well. So let's just do a simple one, the forward difference formula, yx plus h minus yx over h. With this, we can approximate the derivative. That means we have to take some h in the neighborhood of x. X can be also fixed at some point. We have to fix this, and then you take h in the neighborhood, get this difference, which you will say that this is my approximate value of the derivative, and you have exact derivative anyway, which you can get at that particular x. Well, the error between this approximation and the actual, when you draw in the computer, so you will use this formula in your computer at x is equal to some 10 or something. I have actually forgot to mention here. I think this is some x is equal to 10 or 1. I do not remember. Maybe it will appear here in a minute. So I just calculated this in the computer, and exact value, the difference is plotted here. Now what you see? You see that your h, this is your h is decreasing in the left side. So I started with a very large h. You have a pretty big error. Then I have taken a small h, where my error is reducing. Very good. Reducing, and reducing, which is expected, that your h, as you are reducing your h, your error is reducing. Yet that means you are getting a better approximation of your derivative. However, what you will see, you can also draw in your lab tomorrow. What you will see that if you reduce further your h, and you are supposed to get a better answer, because we know that error, the leading term was like h something, and this h is less and less and less, and then you are getting less error. It's supposed to continue in this way, but this is not the case. After some h, if you reduce your h further, the error started increasing. And this is not particular, this is what I'm trying to give this message, not just particular for this particular case. In general, when you solve your differential equations, when you solve your PD, again, you will be playing with this h, and you will realize out of sudden that if you reduce your h further, then the error, instead of decreasing, which is expected, it has started increasing, which is, you have to answer this question, that why it has started increasing. So with this example, I can give you some idea which will help you to understand such phenomena. So I hope you understood the problem. So I have started with some h, some big h here. I reduce my h and h. The total error and difference between this and this was reducing, but after certain h it started increasing. And we have to find the reason for this. First of all, when you are storing when you are evaluating this yx plus h and yx in your computer, it is stored at again, there is a further approximation to this, because you cannot store exactly what you are evaluating there. There is always round off error, because there is no infinity precision in your computer, any computer. So whatever high precision computer you take, still it will round off, and then you will store not exactly yx plus h, but let's say y tilde x plus h you are storing. Here also y tilde x you are storing. So basically, yes, in integration or anything, wherever you have, not just in the integration, I'm talking about by solving PDEs, ODEs, or any other numerical computation you are doing, you will see some such phenomena where you are reducing your h further and further, and your error says that you should get better results, but this is not the case. This is the actual very simple example which you see here in this differentiation case. And so basically your computer is calculating this. That means some perturbed value of this y, some perturbed value of this y and this h, and then it is evaluating this. So y, this derivative is approximated by this, not exactly this finite difference formula, but while calculating in the computer, you are slightly again perturbing those values. Well, I hope you understand. So there are two types of error. One was the truncation error, because you have truncated your the Taylor series, and then you got that approximation. So there is a truncation error, and because you are not able to actually store these numbers, and there is a round off error, which is usually very small, but there is. So, well, now, and this total error which we have plotted here, and this was exactly at x is equal to 10. I have fixed x is equal to 10 here. Now you can see this number there. So this total error is coming. I'm coming to this origin of those errors. I'm just explaining that actually in these slides. So the total error is dy over dx, which is the actual value, minus this which you have evaluated in your computer. So this kind of error I have plotted here. Now, what is exactly the origin? I'm coming to this point, but this is the total error. That actual value, see, when you calculate the actual value also, there will be also some truncation going on, because this x cube you will do, x square you will calculate there. But maybe by hand you actually calculate this and supply that number there, so that truncation error will be reduced. So I mean here dy dx is, let's say, exact, and then you are doing this calculation in the computer, and there is some truncation error happening, the round off error happening, and this is what end result we see, that error which is plotted here. Well, let's just try to do this analysis. Only one slide, not more, and we will get the reason. So using Taylor series, what we have done, this yxi plus 1 is just, this Taylor's expansion here. And then this is what we have learned, that y prime can be approximated by this, and then you have some error there. This is called truncation error. But in computer, as I said, yx will be approximated further because of the round off error. You will not store yx exactly, you will store some y tilde. That means you are computing, you are introducing some error again, that yxi plus 1 is y tilde plus some error, so maybe very small error because of this round off. This is e, I'm denoting by e, but there is something so-called round off error. Similarly, when you store y, you have introduced some error. So instead of y, you have stored y tilde, and there is some error left there too. So if you now see y prime xi, this is what your computer will give you. You substitute this y and y here. You substitute here in your formula. So you are coming with this plus this with ease, and some this local truncation error. So your derivative is equal to this number which your computer will give. Then to have this equality, you have some error introduced because of the truncation, because of this round off, and this is because of the Taylor series truncation. So I'm calling it like true value, finite difference approximation, round off error, and truncation error. So there are two errors, not one, round off error and truncation error. Suppose your round off error is bounded by some epsilon. Epsilon may be very small. Yeah, usually it is very, very small for all I. And this round off truncation error is, if I say this double derivative is bounded by m, so I can easily bound this. So then the total error is given by, here 2 epsilon by h will come because of the round off error, and this m h by 2 will come because of the truncation error. So my total error here is bounded by 2 epsilon by h and some constant into h. Now you see the origin. So because of the round off error, because of the truncation error, which is m by 2h, if your h is small, your truncation error will be small, no doubt about it. You make your h small, your truncation error will be small. What about this 2 epsilon by h? When h was large, well, this was not dominating. This was a small, very, very small number. And this was dominating, and you will see the effect that your error is decreasing. But when you keep on decreasing your h, definitely this is reducing. But for small values of h, 2 epsilon divided by h, this has started increasing. And there is some threshold h where this error, the round off error, dominates now. Right? This dominates. And this is negligible. And this is creating that, graph to increase again as a total error, which you will see at the end. So this is the origin. It's a simple theory. With this example, I have given you some idea, but this exists everywhere. This round off error exists everywhere, not in this particular problem. So you have to be careful. If you're not getting very expected results, don't worry. You think about this round off error also, and then of course there are remedies and all, but this is separate lectures which I can offer, but not here now. Well, so with this, I think I can thank all of the participants, and if there are questions, of course, I will be, though I have answered few in between whatever I have seen, but there was one when we implemented the Gauss quadrature in finite element formulations, 3 Gauss points method is used, but I have no idea how they are derived. I think I have given you the idea how 3 points Gauss quadratures are derived, and in fact more general, not the 3 you can derive with 4 and 5. Of course, the background, how those formulas are coming and all, one has to learn, but at least you got the idea, I guess, with this lecture. So are there some more questions which I did not address? Then I'll be happy to address. So otherwise, I thank you, and I welcome your questions again. Yeah. I can share these slides if you like, so the coordinators can please send me an email if they want PDF of these slides. I can share if they are useful.
Am I audible now?
Yes, you are audible now.
Thank you, Professor Jiten Kumar, for a very nice and informative lecture. And the participants have written a few queries, a few questions in the chat box. And the one person has written, when we implemented the Gauss quadrature in our FE formulation, 3 guess points method is used, but I have no idea how they derived.
Yeah, so I have
So
answered
this is a question by Mr.
Yes.
Surya Rao N.
Yeah, I just answered because see, now we have even not for 3 points, you can use 4 points and all. So now you got the
Professor
idea.
Jiten Kumar, can you hear me? But my voice is not coming.
No, your voice is coming to me now. At least I can hear well.
Professor Jiten Kumar, there is a question in the chat box.
Yes, I have seen almost all questions.
Okay.
And this 3 Gauss point method. So I have mentioned in my slides that not 3, in fact 4, 5, whatever, you can derive those formulations. So that is already there in the slides now. I think the question was asked before I introduced those general formula. So this is answered already. And all other also, which I see that it is, I have answered actually most of the questions. Hope I did not miss anything.
Okay. Thank you very much, Professor Jiten Kumar. Participants, still, if you have any question, you can quickly write in chat box. If you want to ask any question to Professor Jiten Kumar, you can write in the chat box.
Thank you, Professor Kumar, for nice lecture.
Thank you. It was my pleasure. Yes, we have to avoid round of error, and there are various ways actually to go. We can't control completely because there is no way to avoid this. But yes, there are certain fixes which one can do to avoid round of errors. So that usually I have a lecture, but different lecture, which again goes for about an hour, where I usually talk about errors only. Good. So no other questions. So I really thank all the participants listening to this lecture. Yeah. Thank you so much.
Yes. So if there is no more question, let us thanks to Professor Jitendra Kumar for a very informative and very nice lecture about the numerical integration and the numerical differentiation. And Professor Vikas Gupta, your voice was not clear. Would you like to say anything here?
Okay, some audio issues. How my lecture was clear? I mean, there were no audio issues, right? In between.
Yes, sir. There was no audio issue. It was, your lecture was all the time. Voice was very clear.
Oh.
Only one time there was a sudden drop of the voice, but it was only for a couple of seconds. After that, it recovered. So there was no issue at all. Very nice lecture, sir. And I express my gratitude to you for delivering continuously for 2 hours the session.
It was my pleasure.
Yeah, it's not so easy to speak continuously for 2 hours because yesterday and today in morning also I took 2 sessions. So I can understand the pain which you have taken for our participants. So I express my thanks to you on the behalf of all the participants and on the behalf of the organizing committee. And one more request to you, sir. I mean, please send your the PDF file of your PPT.
Yeah, sure. I'll send immediately.
Yeah. So that now, because we have this trend that just after completion of the session at the end of the day, we will be uploading all these materials on the canvas, and this will be visible to only the registered participants, so that they can again see and they can be benefited by our lectures.
Yes. I'll share just in a minute.
Yes, sir.
Thank you so much.
Yeah, thank you so much, sir. So participants, now I'll just close this. I will close this session, and now I will do my homework, like to upload all these lectures on the canvas and to upload the link for the YouTube channels. All the lectures are recorded on YouTube, and the link you can see on the canvas, so that those who have missed the lecture, or suppose you have gone somewhere for some work, then you can again see all these recording of the lectures, and then you can take the notes also of that. Thank you all. Thank you, Professor Jitendra Kumar. I'll be closing the session now.
Yeah, thank you.
Yeah. Good day. Bye-bye.